Okay.
We are proving the hockey stick identity using a block walking argument. And I don't know how much of a proof this is going to be, because all we're really doing is drawing pictures on it. So let's pick something concrete. Let's say that we're going to we're going to find this entry in Pascal's triangle.
You'll have to use these.
Right, but let's argue abstractly why
You have to use those.
if I take each of the 4 orange things,
5.
correct, 5, very good. Why is it that the 5 orange numbers add up to the red number? And I'm saying why in the sense of let's
Why?
think about paths.
Like
Okay.
these.
Now you remember Pascal's triangle. The numbers can be interpreted in terms of paths. Okay? Let's illustrate that concretely. Meaning this is like a 1 and a 1 and a 1 and a 1 and a 2 and a 1 and a 1 and a 3 and a 1. No, not a 1 and a 3.
A 3 and a 1.
And this is a 6, okay?
Okay.
So let's think about why is this number a 6 in terms of paths? Okay? Well, let's zoom in, okay? How many ways are there to get to this location? How many ways are there to get to the location that I've circled in blue using paths? You looking?
Yes.
How many ways are there to get to this location using paths? So go ahead and trace them out.
Okay. Using the pointer?
Yeah, using paths. 1.
Okay, that's enough.
So this is one way. This is another way.
Okay, so let's go in an orderly fashion. 1, 2. Do you want to go over them in some color? They'll probably.
No.
Okay.
It's fine.
1, 2, 3.
Is that it?
4.
What did you just do? You went from here to here?
Mm-hmm.
Drove off the road.
Oh.
Right? This is a street where, this is a city where these are the roads, right? And they're all one-way streets.
Oh.
And you can only go this way or that way.
Oh, I thought you could go like this. Whoops. That's not what I want. I meant the pointer. Okay, that's good. I thought you could go like that.
No, you can't.
Can't.
No.
And cut.
So the question is now, how many ways are there to get to this
there.
location? So we agree that 1, 2, 3.
3.
There are 3 ways to get to here. Not a coincidence
I
that
have
this
another
number
one.
is 3.
I have
What's
another
that?
4.
You can't go backwards.
Oh, darn it.
These are all one-way streets.
Wow.
Because that would be like, in terms of choosing, that would be like, okay, I chose 3 committee members, and then I changed my mind.
And then
And I went back to 2, and then I said, okay, you know what? You're
I
fired.
like this person more.
Yeah. That's not, maybe that happens in real life, not in our made-up math
Thingamajigger.
example. Okay, how many ways are there to get to this spot? 3. Right? I'm going to color them out,
Not a coincidence.
okay? So let's do,
You already used purple.
no, I'm going to use yellow. You're going to be mad.
I'm not going to be bad. But
1,
oh, it's thick enough.
2,
2,
3.
3. Yeah. We
Okay.
need blocks.
And then let's do, I don't know. what's
Okay,
it
you
gonna
can use
cost?
yellow again.
Let's do rainbow. There.
There. Wow.
1,
This is a good program.
2, 3.
3.
Okay, So that means that there are 3 ways to get here, and there are 3 ways to get there. Now, if my plan is to get to this location, I've got to get to here first or to here first.
Okay.
Do you agree with that?
Yes, can't.
There's no other way to get there,
No way.
right?
You got,
Now,
you can go like this, but you got through this point. You can go like
Exactly.
this, but you got through this way. Yeah.
so how many ways
It's
are
guarded.
there? How many ways are there to get to this location? Well, it's exactly the number of ways to get to this location plus the number of ways to get to that location. Right?
Yes.
And we counted that up as 3 and that up as 3. 3 plus 3, 6. Okay? So that is the block walking argument that this entry is 6. Okay? So I just wanted to illustrate the block walking concept of Pascal's triangle very clearly with a simple example. Okay? Now, okay, we've now reviewed conceptually why this red dot, why the number in Pascal's triangle is equal to the number of different paths that I can get. You know, maybe I do like this all the way down to the red dot, right? Maybe I do this all the way down to the red dot.
Red.
Okay. At some point in my path to the red dot, I have to make my last right turn. Okay, and a right turn means going this way.
Okay.
Instead of, we're not thinking about going this way. That would be a left turn. Okay?
Okay.
What happens if I
can't
make...
go left in a hockey stick.
Hmm?
You can't go left in a hockey stick.
What do you mean? So let's say I've agreed that if I'm here
Okay.
and I want to get to here,
Okay.
I'll start over. If I'm here and I want to get to here,
Okay.
and I don't want to go through any of these points, I've got to make a right turn and then finish out my trip.
Okay.
If I am here and I want to get to here,
Okay.
and I don't want to go through these 2 points, I've got to make my last right turn and then finish out my trip.
Okay.
Okay? So we're thinking about, all right, maybe I make my last right turn and then finish out my trip
Okay.
from this spot right here.
Okay.
Maybe I make my last right turn from this spot right here and then finish out my trip.
Okay.
Okay? One by one, we can go through each of these spots and say, okay, once I'm at that spot, the way that I'm going to get to the red dot is I'm going to make my last right turn and then I'm home. Okay?
And you're home?
Now, if I'm going from this point, there's nowhere to go. I just make my last right turn. Okay? So, how many paths are there to get to this spot right here? Well, I could go to this spot, make my last right turn, and finish the trip,
You have this one.
right?
You have this one. So that's 3 so far. 4 and 5.
Well, not 4. What it is however many ways there are to get to here. Plus however many ways there are to get to here.
Here, 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 and here.
Right? What does the hockey stick identity tell us? The hockey stick identity says, if I add up all these numbers, I get this number.
Okay.
What I'm telling you in terms of path walking arguments is that how many ways are there to get home? Well, I can either go here and then finish out my trip, plus the number of ways there are to go here and finish out my trip, plus here, plus here, plus here.
Okay.
Compare that, I'll say it one more time, to the algebra of just saying this number plus this number plus this number plus this number plus this number equals that number.
Okay.
We're saying that, okay, in terms of driving a taxi, if I want to get to this building, I got to go through one of these buildings and then make my last right turn and go home.
Or like one of these stop things.
Right? Okay, so let's leave that as it is.
Okay.
And remember, this is an argument that the number of ways to get here, plus 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 the number of ways to get there, equals the number of ways to get here. And the way I'm saying it equals that is because I'm saying, all right, at some point, I've got to make my last right turn. And that last right turn has got to come from one of these 5 spots. Okay?
Okay.
All right.